We now look at some problems from section 3.8. So some selected, selection of exercises. First one, I believe it's from section 3.8. The book, I think it's problem 22. And we're asked to find the derivative, so the derivative of y with respect to x, where y is defined implicitly by the following relation. The tangent of x squared y is equal to x plus y cubed. And I chose this example because here we're not actually given a point, the point x comma y, for which you need to compute the derivative. It's just a general expression. So the first thing, I'm sorry, that I wanted to say about this kind of problem is that it's okay that, since we're differentiating implicitly for a reason, because we cannot solve y in terms of x. So the derivative of y with respect to x will be given to us in terms not only of x, but also in terms of y. Okay, so that's not wrong. It's normal. In fact, if we were given a point, we would just need to plug in the values of x and y in the formula we obtained for dy dx, and so this does not contradict what we've been doing before. I mean, this is not something different. It's just a more general expression. So that whenever you're given a point, you can just simply plug in the values of x and y that they're asking you to consider. But in general, as I said, the formula for dy dx will depend on both x and y. It won't just be a function of x. But being a function of y, it's okay. I mean, being a function of x and y, it's okay. Well, one, of course, is a relationship. Again, I mean, the y prime is defined implicitly in terms of another expression. You have y prime on both sides. No, you can actually solve for y prime. But now, again, the difference here between problems like this, where you have a relation like this one, is that your y is defined implicitly, and now you don't have a formula for y is equal to some expression only involving x. So we're going to be able to, nevertheless, this is what we're going to show with this example, we're nevertheless able to solve for y prime, but instead of just giving an expression that only involves x, our expression for y prime will also involve y. Okay, so now let's go to the solution. The solution is, again, we do the same thing. So even if you're confused at some point, or you don't know if you remember things correctly, go ahead. I mean, you know that you have to differentiate when you have something like this, where x and y appears on both sides, and it's not clear how to solve for y in terms of x. Then you just blindly differentiate on both sides, and if you manipulate things, you'll see that you are going to be able to solve for y prime in terms of x and y. Again, the same warning applies here. So this means here that I'm just applying the derivative. I'm taking the derivative with respect to x on both sides. Again, if you remember the warning from last time, this means that I'm gonna be taking the derivative with respect to x, not with respect to y. So whenever you see a y, the derivative is not 1. The derivative of y is not 1. We're not differentiating with respect to y. We're differentiating with respect to x. Okay, so we apply here, so on the left hand side, we apply the chain rule. The outside function is tan, and the derivative of tan is secant squared. We evaluated what's inside, so it's x squared y. And then applying the chain rule, we'll multiply this by the derivative of what's inside. So we apply the product rule here. First differentiate x squared, so we get 2x times y plus x squared, and the times the derivative of y with respect to x, so y prime. This is just the product rule. Remember that y depends on y depends on x. So you have a function of x times another function of x. Y is y of x. And we also have to differentiate the right hand side. And we again need to apply the chain rule. So this is 3 times x plus y squared times the derivative of what's inside. But with respect to what? With respect to x. So this gives us the derivative of x, which is 1, plus the derivative of y with respect to x, so that's y prime. And we get we get now an expression that contains both x and y, but also the derivative of y, or y prime. So now we put everything together. We are interested in the terms containing y prime. So we move everything here to the other side, everything on the left hand side. So you get that, I'm going to write it like this. So 3x plus y. I'm going to write the right hand side and the left hand side now. 3 times x plus y squared. And I'm going to open the parenthesis here. So this is 3x plus y squared times 1. So I'm going to distribute here. And then the next thing is multiplying again this outside function times y prime, and this is what I'm writing right now, times y prime, and then minus the secant of x squared y times 2xy. Remember, I moved all of this to the other side, and so this is what you obtain when you distribute here. And now I have to consider the other thing. Now it has a minus, remember, because we're moving everything to the right hand side. So this becomes secant squared of x squared y times x squared y prime. Since I moved everything to the right hand side, the other side becomes 0. And now we need to group like terms. What we're interested in finding what it is y prime. So we put the terms involving y prime, involving that. So this becomes y prime times 3 times x plus y squared minus the secant squared of x squared y times x squared right. So this is so this is what you obtain here. The x plus y squared, and then you have the remaining term, which is 3 times x plus y squared, 3 times x plus y squared, and minus this last term, minus secant x squared y times 2xy, and all of this is equal to 0. Okay, again, I mean, just take your time to go over my computations here. So simply taking my time to write down everything in detail. And the the important thing here is to notice that this coefficient, what's multiplying y prime, depends only on y and x. Of course, the rest depends only on x and y. Okay, so we're going to be able to solve for y prime in terms of y and x. So what we do is we move this back to the other side. So this becomes y prime 3 times x plus y squared, okay, minus secant squared x squared y times x squared, and this is equal to secant x squared y, or 2 times that, or 2xy if we want, 2xy minus 3x plus y squared. So we can now divide by this to obtain that y prime is equal to 2xy secant of x squared y minus 3x plus y squared. All of that divided by 3x plus y minus secant squared x squared y times x squared. And this is a formula this is the formula that we wanted. This is exactly what we were uh, after right here. Formula for y prime that will only involve x and y. And this is exactly what we have on this side. Formula depends only on x and y, no y prime. Please check your computations to make sure that everything is right. I'm doing the same right now, so I'm gonna be making sure that yeah, everything seems to be fine. The only thing, I mean, don't uh, don't be worried if your expression looks is slightly different from this one, because if you flip the signs here, say, and here, this expression is completely equivalent to the other one. Just means that I multiply by minus 1 and minus 1 divided by minus 1, this expression. So please, I mean, I advise you to go over this example and to write down everything carefully and go over every computation very carefully. Now, how does this work in the previous problems? We were given a specific values of x and y, a specific value of x and a specific value of y, and so we would simply just substitute this here and here. X takes in a certain value, say 0 or 1 or 3, and then y would be, I don't know, y equals 1, or y would be equal to 1, or some other number. And each one of these expressions depends only on x and y, no y prime. This one, neither this one, and this is again just a function of x. So this is quite why, I mean, this is another kind of problem that you may be asked to solve, where you're given an expression, a relationship between x and y, and then what you want to do is to what they ask you to do is to take to find the derivative of y in terms of derivative of y with respect to x in terms of x and y, which is exactly what I just done. Okay. So the same, I mean the principle, but the only difference here between the other problems that we went over before is that we're not given a specific value of x and a specific value of y. So you just want to solve for y prime in terms of x and y in general. Okay, so that would be it for this kind of for this part of the material. Now we need to cover something slightly different, which actually can be deduced using the chain rule. Everything, I mean, the implicit differentiation and this thing are all parts of the applications of the chain rule. So what we're gonna do in next, and we're gonna do next week, starting next week, is to obtain the derivatives of trigonometric functions. So for instance, x of arc sine of x. This does not mean this. It's not the same as 1 over sine x. This is just notation for the inverse function of sine. So this is not the same as that. Okay, they're not equal to each other. This is just notation. I could have used something different here. Sine square. I mean sine circle of x. But it just means that this is just notation for the inverse of sine. And we're going to see that this derivative is equal to 1 over the square root of 1 minus x squared. And the derivative of cosine with respect to x, the arc cosine, is minus this expression. And notice here that even though these two things are trigonometric functions, that their derivatives are are very simple functions. So the square root of a polynomial, say 1 over the square root of a polynomial. The same thing here. I mean 1 over the square root of a polynomial, then minus 1. And this issue here with the signs, of course, they're not the same. Otherwise, they would have the same derivative, which is not possible. They're not the same function. But this is what you're going to see every time in all the formulas, all the other formulas that we're going to be going over. So whenever you have the kind of conversion of another expression, you're going to flip the sign. So if you have arctan, arccotan, they're going to look pretty similar except for for this minus sign. It's going to be a minus sign in one of them. So that's what we are going to be doing on next week. And the idea here, how do you use the chain rule here? Well, here you can say that y is the inverse function of sine of x. So it's y of x is the inverse function of sine of x. And so here we can apply sine on both sides and get sine of y, and here we have sine or arc sine of x. And what is this equal to on the right hand side? Can you tell me? I mean, I often ask this question to students, and sometimes I'm fortunate to have people who remember what the inverse function is. Sometimes I'm not that lucky. I don't know what kind of group I have now at this moment. But in case you forgot, if you have a function here like this, you know, function goes from this from R to R, and so you have a value of x here, and this is mapped to this height. So this height is your y of x, or f of x. When we're trying to find when we have the inverse, what we're doing is actually going the other direction. So we're given a value of y, and we want to see where that value comes from. So we're interested in this this number over here. So this is f inverse of, say, suppose this is or yeah, or z or y hat. Then f inverse of y hat is this number right here. Why is that? I mean, the question is, what is the inverse of f evaluated at y? Is the value of x such that x gets mapped via f to that y hat. And how do we find this in the graph? Well, we just go backwards. So this is y hat, and this is attained at this point. I mean, you see that this at this point the graph has height y hat, and this if you go down now perpendicular to the other axis, you'll find the value of x such that f of x is going to be mapped to that height. So if you do this, I mean, if you look at this process and you see what is f of f inverse of y, so if you start from, say, from y hat, you go down, so that's computing f inverse of y hat. But then if you apply f again, then you go back up here and end up where you started. So y. And the same thing here holds for the f inverse of f of x. So f of x is something like this. So this is your x, or some value here, and you send it somewhere. And this here is going to be f of x. What happens if we apply the inverse? We go back to this point which was x. So the inverses have this property that f composed with the inverse is going to give you what's inside, and f inverse composed with f is going to give you what's inside. And so now with this observation, what is this going to be equal to? So you're applying f to f inverse of x. So that's going to be just x based on what we just said. F here of f inverse is equal to what's inside, so y. And that's equal to x. So what about the derivative of y with respect to x? We differentiate on both sides, and we have to use the chain rule. What's the derivative of cosine? Cosine is the outside function. The derivative of cosine, you have to evaluate it at what's inside it, it's just y. Don't forget this step now. Cosine of y times what? The derivative of what's inside with respect to what? To x. So this gives us y prime, and then we have the derivative of x with respect to x is just 1. So y prime is equal to 1 over the cosine of y. Okay, but we want everything in terms of x. So what was y? Y was arcsine of x. So cosine of arcsine of x. This is y. I mean, this is what we used, right? So this now becomes, and here, well, there's nothing you can do, just like this, because this is cosine, not evaluated cosine, I mean, our cosine of x, but cosine value is an arcsine of x. If we had a sine, then we would be done. But okay, we're gonna actually do this next week, so don't worry about it for now. But this becomes same as 1 minus sine squared of sine inverse of x. So we're gonna do this in more detail in a much more geometric way next time. So this becomes 1 over, and sine squared of sine inverse of x. We have the sine of the sine inverse of x, which is just x, and you're raising it to the power of 2. So you get 1 minus x squared, and that is the derivative of sine. Again, we're gonna derive this. So I mean, this equality here just comes from the geometric identity. Sine squared x plus cosine squared x is just 1. But we're gonna do this in more detail next time, and we're gonna learn a much more visual way of thinking about this. I mean, how to transform this this expression here into something involving only x. Okay, so this is much easier for you, I think. This is more geometric, and so this is, I mean, this is where we stop this week. We're going to continue with section 3.8 the next time, and we're going to cover section 3.9 and 3.10, which is the last, which is the next section after that. We're going to cover all these three. I mean, we're going to finish this one and cover the other two next time. As I said, those are still applications of the method. I mean, of the chain rule. I'm sorry, chain rule, which allows you to take derivatives of composite functions. Here we use it because we computed the derivative here of y with respect to x by differentiating sine of y. Okay, and then solving for y prime in terms of y and x. Here this just depends on y, but so that's allowed. And then at the end we went back to this expression. I mean, we were able to go back to the relation satisfied by x and y, and we were able to derive something that only depends on x. It's kind of pretty magical again if you think about it, because this just only depends on x and not on y, and in a very simple form, it's taking the square root of a polynomial. So you're differentiating a very complicated function such as sine, I'm sorry, and then you end up with something very simple that doesn't involve any three functions at all. That's the case. I mean, we're going to see the rest of these derivatives next time.